Hello everyone. In this video, I'll talk about ATR, FTIR, and how exactly it's different from a normal FTIR or normal infrared spectroscopy. I'll talk about the theory and how light behaves in this specific condition. Well, let's go ahead and get started. So, as you know, when we have typically this kind of setup, it requires two different medium. Let's say we have a glass here, and then we have like normal air. So I'm just going to say this is the first medium, glass, and then the second medium is just an air. And then, so when the light passes, when we apply light, when we apply light from the bottom, what does it do? The incident light, it crosses the interface, and then between the crystal and the air or surrounding or medium, and it's refracted. And it's refracted. And that refraction passes through and then changes the direction, and that typically follows a Snell's law. Hopefully I draw it properly. So its refraction is typically like that. So it's the light actually bends here, and it follows Snell's law. So if you want to know about the Snell's law and refraction, please visit my previous video where I'm talking more in details about this specific theory. Refraction. And we can actually measure the angle as well, the angle of incident light. For that, we going to draw like this the vertical line, and the angle of incident we call it with respect to the horizontal line. So if this in this specific angle of light, when it penetrates the medium and then it gets refracted, so it's called refraction. So as this angle of incident increases, we say we reach this special condition, and it's known as critical angle. So let's draw how the critical angle look like. So when we have again our glass, it's the same. Try to draw in the same dimension. So we have a glass again, and then we also draw this horizontal. Vertical line here. It's just imaginary vertical line. So what I'm talking about is when the light now it's a little bit higher, the incident light, then when we increase this, you see here we say we have certain angle. Let's say if this is like 45, and here now we have 60. When we increase that the angle, now what happens is it's a special condition and known as critical angle. At this exact angle, the refracted beam no longer propagates or passes through into the second medium. And what happens is instead it travels along the interface. So this is how it looks like. It travels along the interface like this. So I draw it in a red pen, so just to correctly visualize this. So now it doesn't bend like that, it doesn't pass it through, but it goes just along this the two interface between air and then between glass. So again, we have here air, and then here we have also a glass. So this is what we know as a critical angle. It's called critical angle. So what happens when we keep increasing this angle? When we keep increasing this angle, if we keep increasing that number, when it goes greater than critical angle, the light is no longer transmitted at all, so it doesn't go anywhere, and instead they say it completely reflected back into the crystal, and that phenomena is called internal reflection or total internal reflection. Let's draw it actually. So I'm just gonna first, for clear visualization, just gonna draw here the line, because from now on we're just gonna talk about this. The third one that I just mentioned is the total internal reflection. So here we have again the glass, and now what we're doing here is I'm just gonna draw our this vertical, this imaginary line. So what we're doing here is we are increasing this critical angle or angle of incident now, like that. I apologize. So it's just, it should a little bit bend because it's coming from the air, and like this, yeah, critical angle. So now the critical, it's the angle of incident is a little bit higher than critical angle. So now what happens is, as I mentioned, it reflects back, and this is called total internal reflection. So now our angle is higher than and right here, higher than critical angle. So this is called total internal reflection. So in this specific situation, what happens is when there is total internal reflection occurs, the electromagnetic theory tells us that the electric field cannot abruptly drop at this interface. As a result, a special electromagnetic field that's called evanescent wave is generated. So evanescent field is generated right here at this interface between air and the glass. So that evanescent field, they use it to excite the molecule. So this is called evanescent wave, or they call it evanescent field. So that evanescent field is generated due to total internal reflection. Total internal reflection. And then total internal reflection, the major requirement here, this the angle of the incident angle should be higher than the incident angle of the critical angle. So higher than, I'm just gonna write critical angle, and at that point then you can see the total internal reflection. So what is evanescent wave? So evanescent wave, it only exists under total internal reflection, and it extends a short distance into the sample. So let's say we have a sample here, so I'm just gonna I will erase this. So I'm just gonna redraw the evanescent field, which is right here. And then when we have a sample, typically samples will be like immobilized or they put right here on that glass, on the material. So if we have a sample here, I don't know, that maybe benzene, so, or some kind of organic. So what happens is it short distance in the sample, and then it excites this sample very, very, very slow, and it's a non-propagating electromagnetic field. So it does not propagate like a normal light. So the normal light, if you shine, it will just propagate. It goes up, up, up. But here, it's exponentially, it decays. It decays exponentially with the distance from the surface. So typically, this field penetrates about, let's say, 0.5 to 5 micrometer, and then it just decays. So the exact penetration depends on the wavelengths of the infrared light, the angle of incident, and then the refractive indices of both crystals and the sample. So it depends on two, three options, the details. So let's review the difference between propagation and non-propagation here, because I keep saying that this evanescent field is a non-propagating field. So remember, in transmission infrared spectroscopy, the light propagates through the sample and then carries the energy forward. So when we spread the light, even in a different spectroscopy, even in UV maybe, it penetrates the sample and then it passes through it. In ATR, the evanescent field is non-propagating. It remains confined near that this interface. So, and then it just decays it. That's why they call it non-propagating, and it rapidly decays. This is why ATR FTIR is inherently a surface-sensitive technique. So it all depends on the surface, the excitation of the sample and absorption. Everything happens on this surface between this glass or crystal and air. So we may ask how molecule absorbs. So I just briefly mentioned it earlier, but I'll just go through one more time how exactly it absorbs. So when we have, again, I'm just going to redraw here. Our crystal, and then of course we have the total internal reflection. So it goes in that direction, it comes back there. So we have a sample here, so and then we have here a small light that's propagated, and then when we have the molecule, even though the evanescent wave does not travel through the sample, it still has an oscillating electric field. Molecules located within that penetration depth can interact with that field. So if molecule should be somewhere here located, so somewhere here located to absorb that light. So good contact between the sample and the ATR crystal is very, very critical, because the poor contact means fewer molecules interact with the evanescent field, leading to a weak or very distorted spectra. So ATR FTIR is often used instead of traditional transmission infrared spectroscopy because it dramatically simplifies the sample preparation. So in transmission IR and the normal IR, the light must pass through the entire sample. The sample thickness must be carefully controlled, and then sometimes the strongly absorbing or opaque sample are difficult to measure. In ATR, or attenuated total internal reflection, minimal or no sample preparation is needed, works well with solid, liquids, and powders, and then it's ideal for opaque and highly absorbing materials. So, final takeaway in summary, the ATR FTIR works by using a total internal reflection inside a high refractive index crystal to generate this evanescent wave in the crystal between the sample interface. The evanescent field penetrates a few micrometer into the sample and then excites the molecules or vibration, and then it loses energy when the absorption occurs. So this is how ATR FTIR works.